On behalf of Cenosco, it is my pleasure to welcome you to our 28th Asset Integrity webinar. My name is Elsa Tosma, I'm the lead technical writer at Cenosco, and I will be hosting this webinar. Today, we're going to dive into the world of LNG. We're pleased to welcome Cenosco's domain expert, Amit, to this discussion. Amit is based in Melbourne, Australia. With more than 17 years of experience in the field of asset integrity, he helps operators realize value through the implementation of Cenosco's IMSPI. Hi, Amit, how are you?
Hi, Elsa. Hi, everyone.
Um, Good. And then I would like to welcome Ahmed. Ahmed is an asset integrity professional with more than 2 decades of comprehensive experience in the global energy sector. Throughout his career, Ahmed has managed a full asset lifecycle. He currently is asset integrity leader at United Gas Derivatives. Hi, Ahmed. How are you?
Hi Elsa, hi everyone.
Okay, so today Amit and Ahmed will share their experience or their expert insights on managing the mechanical integrity of LNG facilities. We'll start by looking at why LNG plays such a crucial role in the energy transition. Next, we'll explore the LNG supply chain, zooming in on each stage to examine key integrity management challenges. Then we'll also provide an overview of the industry, focusing on some important economic considerations. From there, we'll shift focus to the LNG plant itself. And finally, we'll dive deeper into the common materials and the degradation mechanisms, highlighting practical approaches to ensure mechanical integrity. Following the discussion, we'll open the floor for questions. We've already received a few in advance, but please feel free to drop any additional questions in the chat. Lastly, please note if for any reason you experience a bad connection, a refresh of your browser will normally do the trick. So let's get started. Amit, can you tell us why it is so important to take care of the LNG facilities and why it is so important to keep the focus on them?
Yeah, sure. Elsa, thanks a lot for the question. So, LNG facilities poses significant risk due to potential loss of containment, mainly because they operate at very extreme operating condition. The temperature in LNG facilities can go down to minus 162 degrees centigrade. That too at extremely high pressure. So any loss of containment can be extremely catastrophic. So we definitely need to manage the safety risk. And then when we have a good asset integrity program for our LNG facilities, we can help. It can help us to improve the operational efficiencies, helping the operator to generate more revenue. And we definitely need to cater for the regulatory compliance so that we ensure that the operators don't end up paying hefty fines to the government agencies. And with that in mind, maybe I have one question for you, Ahmed. LNG supply chain is a feat of engineering and logistics. Would you give us an overview of the whole supply chain for LNG?
Yeah, I can't agree more, Amit. Yes, as you correctly mentioned, it's a feat of engineering and logistics that is designed to move energy across the continents. It starts, as we can see here, with the raw gas, whether the raw gas it's conventional, whether it's shale gas, whether it's onshore or offshore, uh, deep water or shallow water, different configurations, but at the end of the day, it starts with raw natural gas. Sometimes there are preliminary treatment happens in the offshore before the gas is ready to be piped into the pipeline. So, separations, glycol dehydration, sweetening, scavenging, dew point control, injection for corrosion inhibition and scaling inhibition, stuff like that. Then, when the gas reaches the pipeline specification, then it is pumped or piped through a rigid or flexible pipelines, whether it's going for a floating LNG or onshore pre-treatment facility. Sometimes this pre-treatment facility is a part of a bigger plant. So we can see here that this is the two options, FLNG or pre-treatment facility. Then it goes to the liquefaction plant. So within the liquefaction plant itself, the gas is liquefied. Predominantly, the gas that goes into the liquefaction train is mainly methane. It's from 87 till up to 99% methane. Definitely, there are uh, another components of the gas, C2, C3, a bit of nitrogen, a bit of H2S and CO2, definitely within uh, specified limits. But the LNG train, or the liquefaction train, this is actually the heart of the LNG facility, where the magic happens, where the gas is turned to be liquid. There are various technologies available out there from different licensors, whether it's open or closed cycle process. Probably we'll speak about the technologies later on.
Thanks a lot, Ahmed. Then you did spoke about the pre-treatment unit. You did spoke about the liquefaction unit as well in brief. Just wanted to ask you, what's the importance of gas pre-treatment before the liquefaction unit?
Okay, so there is significant importance for the gas pre-treatment before the gas goes into the liquefaction train. It is mainly to get rid of the nasty stuff and get the gas to be ready to be liquefied and turned to be LNG. Getting rid of water, getting rid of H2S, carbon dioxide, getting rid of the heavier components that uh, and keep only the methane, the lean gas. So definitely, it's the pre-treatment facility is very, very important to the rest of the process. Definitely.
Great, thank you, Ahmed. And then after the liquefaction, in order for the gas, for the LNG to be regasified, to be able to pump to the gas grid, what are the options that normally importers use?
They're actually after the gas has been liquefied and stored in a large tanks. It's normally 100 around 160 thousand cubic meters of LNG that's operating a bit higher than the atmospheric pressure, around something around 10 kPa or something. Those The LNG then is pumped to a product jetty, uh, where actually it is loaded to LNG ships or LNG carriers to export. LNG carriers are kind of ships that or ships that are in double insulated hull, that have double insulated hull, designed to contain the cargo slightly above the atmospheric pressure at a cryogenic temperature around 100, minus 169. It operates around zero point 0.3 bar, something within those figures. So LNG then is received after during at the delivery point. When it is received, it cannot be used in its liquid form. Then it needs to be regasified. So it could be either regasified either immediately or subsequently after it's been stored. So it's based on the availability of the facility. If we can look here on this, so if we look down here, we can see that there is an onshore facility that is containing LNG tanks that where the LNG will be stored. Then it will be regasified. The other option is using FSRU, floating storage, and regasification unit, which is a ship that can be either custom designed or converted from LNG, or converted LNG carrier. Excuse me. So the LNG can be heated afterwards and gasified using various methods like direct fired heaters, like seawater, heated water, or even air. Then the gas is then shipped or compressed after it's being gasified to a compression station, then to the gas grid. So it reached the final customers. So it would go normally to power stations, houses, factories, another type of customers. So the supply chain. There are various players within the supply chain, not a single player, and being harmonized and being able to work together and play together. It's quite important for the smoothness of this supply chain.
Wow, so fascinating. Thanks a lot, Ahmed. Now we would like to understand from you about the whole overview of the whole LNG industry. So, according to you, what's the importance of LNG in the global energy mix?
Okay, natural gas actually would contribute around 25% of the world energy mix. 13 more than 13% out of that is being transferred and in the form of liquefied gas. So it's quite significant. That would put the LNG industry as a major player within the global energy landscape.
Thank you, Ahmed. Now, continuing our conversation further, someone could easily claim that LNG is the bridging fuel for future. How would you comment on that?
Uh, Definitely, I'd agree on that because I see that the LNG is considered as a bridging fuel for the energy transition for a number of reasons. It's cleaner. Why it is cleaner? Actually, there's a chemical reason for that. That methane has a very high hydrogen to carbon ratio. This means that when it burns, it's more cleanly than more complex hydrocarbons. Cleaner than coal, cleaner than fuel oil. So if we look down there, we can see that when LNG is burned, it produces less carbon dioxide emissions, more than 50%, sorry, more than 50% less than coal and 25% less than fuel oil. So definitely it can be considered as bridging fuel as we're moving towards a cleaner energy consumption and cleaner energy mix. So definitely LNG is should be, could be the vehicle for that. Yep.
Yeah, no wonder LNG is the fuel for future. So, with that context, who are the major players in the market, Ahmed?
Okay. This market is if we look at it from the supply and demand point of view, we can understand easily if we look at this uh, diagram there. So if we look at the demand, we can understand that the on the demand side, Asia is the center of gravity, with China, Japan, and South Korea being the largest importers. So those are the biggest players within this market.
Yeah, yeah, certainly, certainly, and it's very well evident considering the consumption pattern that we see in the market. Then, Ahmed, how does the future of the industry looks like, speaking within the context of supply and demand?
Okay, currently, actually, the scale of the industry is staggering. We have around 400, more than 490 million ton per annum that is available online. Liquefaction. I'm speaking about the liquefaction capacity, and we are expecting to have 210 million tons to come online towards 2026. This is actually supported with a big fleet of LNG carriers, 740. And guess what? We have also 337 new vessels that are on the order books of the shipyards. So the industry is getting bigger and bigger. And looking at the number of projects and the liquefaction for the liquefaction capacity that are in the pre-FID, which is the financial investment decision, which is exceeds 1,000 million ton per annum. So we can see that it's really staggering. It's getting bigger. The demand is getting bigger. We can see also that the LNG trade has been growing for the 11th consecutive year. So, and the demand will continue to grow, uh, driven by sustained growth in Asia and driven by sustained growth in North America. And also, if we want to look at the some financial figures, very quick one. So we can see that the prices has been averaging around 11.91. 11.91. That's the Platts JKM, which is the A for the Asian market. Excuse me. Which is actually for the Asian market, the benchmark for the spot cargoes for Northeast Asia. Definitely, there are different benchmarks available, like TTF in Europe and Henry Hub in the United States. But looking at the market itself, we can see that the prices in 2024 has been averaging below what it was in 2023. So it was subdued, but it would remain volatile. We've seen that in the beginning of 2025. We've seen some spikes in Henry Hub and TTF uh, prices. Yeah, and that was also driven. One of the things that is affecting the LNG consumption and the electricity consumption also is a technology. The technology, artificial intelligence, data centers is getting to consume about 1.5 of global electricity use in 2024, and it's getting to be bigger and bigger. So the technology is affecting the consumption. Also, we're expecting a next wave of liquefaction capacity that will come online. Honestly, it is quite complex. It's why it's quite dynamic. Uh, Technology and the consumption is getting higher and higher. Uh, the heat waves is also increasing the consumption. We're expecting online liquefaction capacity to come online very soon. So there is actually a continued risk of misalignment between continuity of supply and realities of demand. So days will tell.
Thanks a lot, Ahmed, for providing us a detailed overview of the LNG industry. It was really, really informative, especially the factors that you have described are affecting the supply and the demand. They were really, really informative for everyone. Now, I would like to understand from you the whole asset life cycle of an LNG plant, how the integrity efforts could extend beyond the life of an asset for LNG facility.
Okay, so it normally starts with looking at the concept and looking at the feasibility of the facility. Is it and at this point there are big economical and technical decisions are being taken in order to that in order to take this decision and take that in an optimized way. There are lots of factors that are being considered as at this stage, including securing the supply chain, including the gas deliverability, the market demand. Is it the right time for building LNG facility or not? Delivering and building a profile, capex and opex, looking at the operational safety, looking at high level, looking at the targeted flexibility within this facility and the targeted reliability. At this point, from integrity and reliability perspective, we'll start looking at setting the outlines for the integrity and the reliability philosophy, setting the overall philosophy. Then after that, we start looking at the process development by taking a closer look at the available options, looking at the uh, LNG is known for having various configurations for the facilities. There are various technologies available out there with various licensors, and comparing those technologies is kind of uh, it's not an easy exercise, but definitely considering the asset life costing, and the cost of keeping this asset and cost of running this asset. One of the important things that should be considered actually is the refrigerant compressors, one of the most expensive assets within those facilities. What are the power consumption? What's the compressor power required? What are the heat exchanging surface area requirements? What are looking at the cooling and the heating curves of the MCHE, or the main cryogenic heat exchangers. It could be only misleading looking at the power efficiencies at this point. It also, considering the life cycle and the cost of owning this asset and operating this asset is quite important. And definitely at this point, while looking into the process development, considering the human errors, considering that we are humans at the end of the day, so trying to select a safer process, easier configuration, more error tolerant, with wider safety margins. This is very important to be considered at this point.
Thanks a lot, Amar, for that. So my next question to you is, what are the main considerations that should be taken care of during the building operations and the maintenance of an LNG facility?
Uh, it's Yeah. This At this point, I believe it's quite important to start um involving how integrity and reliability efforts to be integrated heavily within the engineering or detailed engineering process. And I believe this is the best time where you start setting up the integrity and reliability systems. It's a great time to do baseline inspections. Is a great time to start doing the first run for the RBI, for the RCM, for the RAM, for the ECA. Uh, Definitely, this could be a good start. This could be a great start. Having a baseline, probably doing a baseline at this time, this could save a huge amount of money. This could help you define anomalies and errors during construction, and definitely trying to set the corrosion management program and uh, take into consideration changes that happen during construction compared to the design. Yeah, when it goes then to operation, it makes things much easier. Once you have your reliability and RBI studies and your CCD and IUWs already set, you start tweaking those studies, start tweaking how you see risk, uh, how you going to manage the deficiencies within your facility, how are you going to plan for the turnarounds. It makes things much easier for people managing the integrity and reliability during the operation, which is actually the longest period of the asset life cycle. And actually, this is when the design and the material and equipment are really get to be examined in the real world.
Yep, cannot agree more, Ahmed. Thanks a lot for that answer. So, according to you, what's a typical design life of an LNG plant, and how could a life be extended?
Actually, it varies from design to another, but let's say it's from 25 to 30 years. Those are the typical design life for such facilities. But anyway, we have facilities that the LNG industry has been in the market since the 60s. This is the first commercial LNG. Actually, it was built in Algeria. It's called Camel. I think it was in mid 60s, the first commercial LNG unit. So we can see that once the plant starts reaching its end of life or design life, there are various aspects that need to be taken care of. The first one is related to degradation management, material degradation management. The other one is related to obsolescence management. Obsolescence is actually related to technology obsolescence. Um, let's say I don't have the spare parts, I don't have support from the OEM, I don't have uh, available spare part for critical equipment. The technology is not supported anymore. Uh, all that kind of stuff. So managing the obsolescence that is happening to those facilities over time, this is quite important. The other thing is the managing the organizational aging. Organization is like a human; it ages. Okay, the good people, they are leaving, they're retiring, uh, they're taking knowledge with them. Okay, so succession planning, this is quite important thing that need to be considered, not just in the LNG industry, in any facility. So there are so mainly those three aspects: material degradation and the technology and obsolescence, and the organizational aging, also the transformation that is happening within these organizations, and managing the risk of this transformation. So looking at those three main areas carefully and managing those carefully uh, is quite significant to extend the life of the business.
Great. Thanks a lot, Ahmad, for making us understand the whole asset life cycle of an LNG plant. Now, if you can throw some light on the main process unit of an LNG plant, that would be really great.
Okay, so this is the exciting part. Okay, so so the gas gets in into a slug catcher where actually it separates free liquids. It goes down the free liquids, and then the gas goes up. Okay, so so it first goes to a sweetening unit. The sweetening unit is typically an amine treatment unit. There are various names for these units. Uh, so it's mainly a main treatment unit where amine solvent like MDA absorb acid gases like CO2 and H2S. So definitely those nasty. We need to get rid of those nasty stuff before it continues into the facility. Then it goes to a dehydration unit where we get rid of water to down to zero point 0.1 ppm using mole sieves, as a number of beds that is operating in cyclic modes, adsorption and regeneration. There are different configurations of this unit. It's actually one of the units that it's worth looking at. We'll speak about it definitely when we start speaking about the degradation mechanisms. Then the dehydrated gas goes to mercury removal unit uh, that actually use a carbon bed to get rid of the mercury to prevent amalgamating to prevent the mercury from amalgamating with and destroying plant aluminium heat exchangers that will be available that will be in the upcoming units. Then it goes to the NGL recovery through the end. So the NGL recovery, it could be a shallow cut or deep cut, depending on the configuration you decide to do in the design phase, depending on the gas composition. So at this point, normally the gas is separated. You remove all the heavier liquids, starting from C2, C3, and C4, and downwards is being separated from methane. Only when the methane is remaining, it goes to the liquefaction train. The liquefaction train, actually, this is, as we've mentioned, this is the heart of the facility. Sorry, sorry. So this is the heart. This is the beating thermodynamical heart of the facility, where actually the gas is being liquefied using various technologies. There are various technologies available out there: SMR, DMR, propane mixed refrigerant, cascade. So there are different technologies out there. You got to make the selection as much. You got to spend time doing the selection in the beginning of the life cycle of the project, in the selection of the technology that suits that suits what's the size, based on various aspects, including what is the size of the liquefaction capacity that you're aiming for, what's the power that is expect, because those technologies are different in power consumption as well. Okay, after the gas is being liquefied, it goes to nitrogen rejection. Nitrogen rejection is a unit that normally uses cryogenic separation to get the nitrogen content within the gases less than 1 mole, 1 mole percentage. Actually, for a number of reasons. One of them is to increase the calorific value of the gas, and to make the gas more manageable, um, especially when we're speaking about the boil of gas, and also could minimize risk of some phenomena like rollover, that's known to happen in case of which is a safety risk. Okay, then the gas then is being stored in a liquid API 620 tanks, so cryogenic tanks. Then it goes to the end user through the shipping. If we look at the liquid side, if we start looking at the liquid side, it goes to, so the liquid from the slug catcher, it goes to the condensate stabilization unit, water stripping unit. Probably then it goes to sulfur removal unit. If we look at the LNG, the separated heavier component, then is fractionated further to valuable components like propane and butane. Then it is stored in suitable storage, normally in spherical tanks or bullets.
Great. That was really informative, Ahmed. So maybe we can discuss a bit about the material of construction that are in use in an LNG facility. So, so if you see on the screen, the cryogenic heat exchangers in an LNG plant are mainly made up of austenitic stainless steel, and the plate heat exchangers are constructed by aluminum alloys. The compressors and the associated pipings are typically carbon steel, low temperature carbon steel, or duplex stainless steel. The process vessels are typically austenitic stainless steel, nickel alloys, inconel and monol, and these are to support the low temperature services. The control valves are austenitic stainless steel, and the most unique type of equipment that you would find in an LNG plant that's quite different from the upstream or a downstream unit of oil and gas plant. So this is a typical fixed tube double wall storage tank designed as per API 620, as I have mentioned. And the inner wall of this tank is typically made up of 9% nickel. So if you see the material of construction in an LNG facilities are selected to mainly support the extreme operating conditions of low temperature that goes as low as minus 162 degrees centigrade. So let's talk about some of the common degradation mechanisms that can happen at an LNG facility. So the degradation mechanism at LNG plant could be classified into two categories: age-related DMs or non-age related DMs. Age-related DMs are typically a degradation mechanism that have their degradation rates defined and then they becomes bad as they age. Non-age related typically are a degradation mechanism for which they do not have a degradation rates established, and the degradation can be very sudden as well. So typical age-rated DMs that can happen at an LNG facilities are with CO2 corrosion, with S2S corrosion, amine corrosion, microbiological induced corrosion, caustic corrosion, or aqueous marine corrosion at the jetties. The typical non-age-related degradation mechanisms include brittle fracture, liquid metal embrittlement, caustic stress corrosion cracking, chloride stress corrosion cracking, and amine stress corrosion cracking. One of the peculiar thing to notice for the degradation mechanism at LNG facilities are the non-age-related degradation mechanism, and these happen mainly because of the extreme operating conditions at these facilities, along with some of the impurity that could include metallic impurities like mercury present in the stream that could cause these type of sudden failures in the form of stress corrosion cracking or fractures. So, Ahmed, would you like to add anything to the degradation mechanism that we just discussed for LNG facilities?
Oh yeah, thank you very much, Amit. I think you've covered everything. There are few things that is related to specific types of asset within the LNG plants. Uh, as you've just mentioned, the non-age related damage mechanism. I think here we need to emphasize on the importance of IOW and operating within the integrity windows specifically for LNG. Is known that there are kind of equipment operating there that is really challenging to inspect, like the PAHX, the brazed aluminum heat exchangers, or known as cold boxes. It's very sensitive, very efficient equipment, but definitely it is affected by excursions. So I think working together with operations and looking at the operating limits, delta T, uh, and the formation of hydrogen formation, or this is very important in maintaining the integrity of such facilities. Also, I believe that locations like downstream the refrigerant compressors, small bore piping there uh, would normally suffer from fatigue due to vibration. So I think having a robust small bore management system, specifically around those facilities, is quite important. Also, the dehydration unit, because it's operating in cyclic mode. Thermal fatigue could be one of the issues. Looking at, it's always recommended to look around the inlet and the outlet nozzles of the dehydration beds. Looking at the skirt to shell intersection, specifically for older designs where there is no smooth transition, because there are differences in thicknesses there. It's also recommended to have a look at this at these locations. Uh, uh, there is a significant importance actually in safe in having standard operating procedures, and the integrity people sometimes could be or the integrity of the asset could be affected by those SOPs. Uh, One of the most famous locations for that need to be operated carefully, especially at the startup of the facility, is the round down line. Looking at the round down line, where the liquid gas would go to the storage tank, got to treat that carefully. Got to operate within the got to start up the facility as per the operating standard operating procedures. The nozzles at the top of the LNG plant as well. Uh, you got to look at that carefully because it's concrete, mostly concrete, and then air. So probably some locations would be very similar to a soil to air corrosion. Especially, nobody would love to go up the LNG tanks, right? Is and definitely last but not least, because of those facilities are normally located in the marine environment, you got to be taking care of the external corrosion and everything related to that. So chloride pitting, chloride stress corrosion cracking, corrosion under insulation, painting deterioration, mainly external factors because it's operating in marine environment. I think it is kind of challenging.
Yep. Cannot agree more to that, Ahmed. So that's the reason what I have done. I have decided to go into a bit more detail for three of the critical degradation mechanisms that are very peculiar to LNG industry. And ins- these degradation mechanisms cannot be just mitigated by performing normal inspections such as visual inspection or thickness monitoring. So the first one of them is brittle fracture. So typically brittle fracture is a degradation mechanism which can cause a rapid fracture under stress for the vessels or pipings. And normally brittle fracture is taken care of during the design itself, where appropriate materials are selected, they are impact tested before put into application. But then operations plays a very, very important role in ensuring that brittle fracture doesn't happen when the pressure vessels or the piping is put into service, especially during the startups and the shutdown where process excursions can happen. Brittle fracture remains a potential degradation mechanism that can happen in LNG facilities. So during those startups and the shutdowns, the temperature can fall below something called as DBTT. DBTT is defined as ductile to brittle transition temperature for the material of construction of that particular vessels or piping. And if the temperature falls below the ductile to brittle transition temperature, it's very important to perform uh, non-destructive testing such as in situ hardness or metallography to ensure that the toughness of the material is still intact. The material have not degraded metallurgically, the grains have not become coarse enough. So if they have become susceptible, if they have become coarse enough, then the suitable action needs to be taken because brittle fracture can be extremely rapid. And second degradation mechanism with which can have very detrimental effect and it can be very unsafe is liquid metal embrittlement. And this is very peculiar of LNG facility because there have been past instances where liquid metal embrittlement was observed at the brazen aluminum heat exchanger or the cold boxes as you have described them earlier. So the typical methodology of this degradation mechanism is when LNGs are extracted from the Earth's surface, mercury could be one of the constituents of this stream, and at a certain temperature, mercury can come in contact with the affected material, which could be carbon steel, low alloy steel, or aluminum alloys, and they can penetrate into the metal and they can reduce the metal toughness, thereby exposing them for a fracture. And this fracture can be extremely sudden. So it's very important to monitor the integrity operating windows of the of these exchangers of these pressure vessels. We can track the concentration of mercury, we can track the differential temperature, and if there are any traces of mercury that are found, then we can perform metrography and spectroscopic analysis to confirm the same. So again, IOW plays a very, very important role, and we have to track these parameters for excursion. The third such type of degradation mechanism is again chloride stress corrosion cracking. Sudden. This can also lead to a sudden failure in the operating equipment. So chloride SCC typically happens at the material which are susceptible to chloride SCC. There has to be susceptible environment and presence of tensile stresses. And mostly chloride SCC happens in austenitic stainless steel, and the main cause is presence of chloride at a temperature more than 60 degrees centigrade. So again, here also it's very important to monitor the integrity operating windows for chloride temperature and pH, because chloride SCC is a type of degradation mechanism that is transgranular in nature, and once it starts, then the crack propagation can be extremely fast. It's very difficult to track the progress of those cracks, so the failure can be all of a sudden. So we have to keep track of the IOWs, and if there are any breaches in the IOW, then we need to ensure that we are deploying suitable entities to basically check if there are any cracks that have already happened. Some of the prevention methods obviously could be our IOW monitoring, and then we can also make use of the high velocity thermal spray coating that could be applied on the internal surface of the stainless steel so that chlorides could not come in direct contact with the metallic surface. So those are some of the critical degradation mechanisms that I thought to discuss in a bit more detail. And one of the common point or the common feature in these degradation mechanism is the monitoring of IOW. That's what make LNG facilities quite uh, different than the normal upstream, midstream, or a downstream oil and gas facilities. Uh, so, Ahmad, from your experience, would you like to add further on the degradation mechanism that we just discussed in the LNG facilities?
No, I think you've covered everything. I can't agree more on what you've just said. Um, Thus, I just would like to emphasize on the importance of integrity operating windows. Um, the thing behind this is that uh, sometimes the IOWs are the only mean for ensuring the mechanical integrity of an asset. And there are various examples for that, but uh, specifically in the IOWs and in cryogenic service plants, generally IOW is very, very important. Thank you very much, Amit. It was amazing.
Ahmed, Ahmed, thank you both so much for this insightful discussion. I also have to say the visuals were fantastic and really brought the topic to life for me. I hope that just like me, the viewers have gained a clearer understanding of how the mechanical integrity of LNG facilities can be effectively managed, especially considering the complexity involved. Amit, before you wrap up, would you like to share some final remarks with the audience?
Yep, sure. As you would have seen that managing the mechanical integrity program for LNG is quite different to manage the mechanical integrity program for any refinery, petrochemical, or a upstream platform, because LNG involves dealing with lots and lots of non-age related degradation mechanism. It involves managing material of construction which are not carbon steel, which can have normal degradation mechanisms. So visual inspection or thickness monitoring are not the typical non-destructive techniques that are very much applicable to an LNG facility. So that makes it quite unique in a way that we need to have something quite different than time-based inspection and the normal visual inspections being recorded for these type of facilities. So which brings the importance of IOW. And
Cenosco IMS suite is one such tool in the market that helps us to manage the non-age related degradation mechanism quite efficiently. We can perform RBIs of non-age related DMs, and then we can set up the IOW programs in Cenosco IMS by integrating with the OSI pipe and the other historians, and have the limits defined to track the excursion within IMS. So it is a complete tool that helps us in managing the mechanical integrity program for LNG facilities.
Okay, Ahmed, would you like to add something?
Finally, honestly, I want to say that it's the we've seen that the landscape of the LNG supply chain. So depending on in which part you're operating within the supply chain, whether you're operating a liquefaction plant or gasification plant, FSRU, floating LNG, or even LNG carrier, each part of those assets or each piece of equipment is having its own integrity aspects, is having its own um, damage mechanisms, having its own way of managing its mechanical integrity. Uh, if I can only say one recommendation, it would be the earlier the better. Start early with asset integrity. Start from design. Don't wait till the facility age. Then you start thinking of asset integrity. Start early, and definitely you will realize the value. Thank you.
Good. Um, so, unfortunately, dear viewers, we have reached the end of our time today, and we won't be able to take any more live questions now. However, um, I really believe many of your questions have already been addressed during the discussion, but I promise we'll review any of the remaining ones and we will get back to you with the answers. Also, we will definitely be sharing the slides with those amazing graphics or visuals. And we will also include the references which I've just shown in the screen earlier, so that you can also explore the topic further at your own pace. So Ahmed, thank you again. Um, Also, all the viewers watching, thank you for your time as well. Please take note that the webinar will soon be available to download from our website. And then before we close, just like to share that we are already planning a next webinar. And this one will focus on the latest features in our IMS software. It will take place in November, so please stay tuned. Thank you.
Thank
Thank
you.
you.